Yeah. So the thing is, after completing the class, actually, I provide the video link and also the like the presentation that I am going to present in front of you. Everything I give it to the NPTEL committee, right? So it is like that. They will circulate that to you first of all. Like other than that, this the same video, whatever I will discuss today, will be uploaded on my YouTube channel as well. So the YouTube channel name is Tanmoy Khan, Tanmoykhan. That is my name. Tanmoy Khan, PMRF IIT Kanpur. You can search it, right? So there you will be able to get all the video lectures. In the last week video also I have already uploaded there. So today's after completing the class I will upload there, right? So it is very much possible for you to go there and like the subscribe the channel if possible, or you don't need to, just you can watch the video. So I'll just show you the channel itself so that it will be very it will be easier for you to find, right? Showing you. So are you able to see that? This is the channel. So this is the first video I have already shared. Are you able to see the screen? Hello?
Yes, sir. It's
So
been visible.
yeah, this is the channel, right? So here I will upload. So you just need to search by the name and you can get the videos. There I have also taught some other videos as well. But like there will be a specific playlist for surface and interfaces NPTEL so that you can access all the videos. And also PM as so like the NPTEL will also share that what I feel. Okay. So let's just start the presenting, yeah, for the class right now. So people will join and I'll try to admit them at the time. So let's just start the today's class. So yeah, am I audible? Right? Yeah. Let me just. Yeah. So in today's class is about the solving the assignment number two. Okay. So in this week, and the week two basically. So am I audible, right, Avinash?
Yes, yes, sir.
Yeah. So in the week two, through the lectures videos, we have learned about mainly the adsorption, absorption kinetics, and adsorption thermodynamics, like how the energetics are, how one can define add layer specifically by using Wood's notation, matrix notation, and all that. So in the questions basically are from that thing as well. So we need to like we will try to solve that questions. But before going into that, I will try to give you a very basic introduction about what is adsorption. See, right? So these you know maybe, but just for the sake of it, I'll try to introduce what is adsorption, what is the basic difference of adsorption and absorption, and then very little bit about Physisorption and chemisorption, and then we'll go to the actual questions that have been given and try to solve that, right? So I think there's no problem. So in the first week itself, we have talked about surface reconstruction, right? We all know. In the last class also, I tried to explain it a bit. So what is surface reconstruction? Because in the surface, the molecules are having lesser coordination number and lesser like interacting atom nearby. So it tried to minimize the energy, and that is called surface reconstruction. and it can happen in three way, like a relaxation, like two surface atom can come closer, or two more than two can come closer, so that one of the atom can be missing. So there are some possibilities by which surface can reconstruct. But if you think why it is reconstruct, because like the surface is actually having, like if you think about, this is a surface, let's say, this is about surface molecule. This is the first layer. This is the surface. This is your surface, and there will be a layer next to it, and there will be much more layers next to it, like that. Like so, if you think about, let's say, this atom. So this atom is getting interacted by these, and these. So in every possible direction, actually, it is actually getting even the coordination number is 1, 2, 3, 4, at least 4. So it is having actually higher coordination number, and it is actually getting interacted by more number of atoms, like in every direction it is actually interacted in a similar manner. So the net force in a bulk atom, right, will be somewhat like bulk, there will be no net force, right? But if you think about surface, it is actually getting interacted by all the atoms are besides them and beneath them, but there is no atom in the outside. So it is automatically having lesser number of molecules, like lesser number of coordination. So due to that, it actually go reconstruction. But let's say if some another foreign atom can come here, so there will be a bit of stabilization, right? So the black molecules are, if you say these are foreign molecules, so if some foreign molecules come nearby this in the surface, so this molecule will be now get some kind of stabilization. I'm not talking the total stabilization, but it will get some, the coordination number will increase. So this is the common phenomenon of surface, by which it try to minimize its energy as well due to adsorption. And this phenomenon, where the concentration at the surface increases, is called as adsorption. So that is what I have tried to write. What is the adsorption? So let me just tell this. So when concentration of substance become higher on the surface of a substrate than the bulk, that then it is called adsorption. But if we think a very common example, like let's take a sponge and just drop it in a water, so it will like absorb very much water from it. So what is this, like how this adsorption is very different than absorption? Then we need to know that. So what is absorption? Absorption is a physical or chemical process in which atoms or molecules or ions can enter the bulk phase, like through every possible points the some foreign atoms are coming. So this is called absorption. But if some surface phenomena, like adsorption is purely surface phenomenon, so the concentration will be increased in the surface only. But in case of absorption, so the concentration will be like uniform overall, uniform throughout the bulk. So that's what I have tried to given some points differentiating between the adsorption and absorption. So what I have written, the surface, this is a adsorption is a surface phenomena, absorption is a bulk phenomena. Now, if we going next to the next point, we need to know. So if I said this is a surface, and this is the foreign atom, or we can call this is add atoms, or we can, so this we call adatoms, or we can call adsorbate. So that means the substance which is adsorbed on the surface is called adsorbate or adatoms or molecule. Yeah, let me just join, like, allow them to join, then I'll discuss about this. Sorry. Yeah. So what I was taking? So the substance which is adsorbed on the surface is called adsorbate, and the on which that adsorbate is actually adsorbing, the substance on the surface of which the atoms are adsorbed is called substrate or surface layer or adsorbent. So this add atoms or add layer. These are the black I am showing here, and this is the surface atom. So in case of adsorption, these are too much substrate and adsorbate specific, because like some atom, this is very specific, but in case of absorption, this that no, not that much specificity actually. So this is less specific. Now in case of adsorption, this is only happening in the surface, so the change of energy is small, but it is actually happening throughout the bulk. So that change of energy is actually high in case of absorption. Also, what I said already, in case of adsorption, this is as it is only surface phenomena. So there will be an unequal distribution of molecules in the surface and the bulk. There will be practically no atom, no that add atoms in the bulk, or that will only be in the surface. But in case of absorption, there will be an equal distribution of the foreign atom, right? So these are the basic difference between adsorption and absorption. Now we need to know why adsorption actually occur, because like there is a surface. Let's say there's a surface, as I said, there's a surface. Now something is coming and sticking to it, right? Something is coming and sticking to it. So if you think about that, the entropy, right? Entropy of the system will obviously decrease. So then how it is actually happening? So we know for any process that follow delta G is equal to delta H minus T del S, where delta H is the enthalpy change, delta S is the entropy change. This is the enthalpy change in enthalpy, and this is the change in entropy, and this is the change in free energy. And if if a process to be happen, so if some process is actually happening, then delta G must be negative. This is the basic requirement of thermodynamics. For any process to be happen, the delta G must be negative. So now we know that surface is actually some add molecules is coming and sticking onto the surface. It is some kind of like that. So obviously delta S will be negative, right? So delta S will obviously be negative. Now delta S will be negative. So if delta is negative, that means the overall term T delta S will obviously be positive, because this is itself a negative, negative and negative. So this will be a positive term. Now we want delta G to be negative. So if the process needs to be happen, that time you have no way rather than delta H of the process must be negative. And it will be so negative that delta H will be given the T delta S, right? So delta H will be much less than T delta S, right? And if you think about the mod value, so just the value if you think, then it will be higher than mod value of T delta S, right? So that means the process will be very much exothermic. And also you think that this T del S is positive. So that means if we increase the temperature, if we increase the temperature, then overall T del S term will increase, and that's a positive. So again, it will go towards like the spontaneity will be hampered. So that means adsorption will always occur in a low temperature, right? So like if you increase the temperature, then add rate of adsorption, not the rate of adsorption, the chance of adsorption will be lesser. That means we know, like if this is a molecule, let's say A, and this is a surface, and this is the process of adsorption. This is the process of adsorption, let's say. So now from A to S, it's one can get A plus S again, and that is called desorption, right? Now, if you think about the kinetics of desorption, sorry, the thermodynamics of desorption. So what is happening into this process? Obviously, delta H is greater than zero, right? Or it is positive. So that time, if you increase the temperature, that means the value of T delta S will increase, and we have a negative. Like this is actually minus T delta S, right? This is actually minus T delta S. So if you increase the temperature, desorption will happen, right? So adsorption will happen at low temperature, and with increasing the temperature, desorption occurs. Temperature increase. Right? I don't think there will be any problem with that. Right? Hello? Are you there? Hello? Hello, you guys are there? Prakriti? Okay. Let me go to the. So now there are actually two kind of adsorptions are possible. One is physical adsorption and another one is chemical adsorptions, right? One is physical adsorption and another one is chemical adsorption. So what are those? I'll try to talk about a bit. So if add molecules or adsorbents are adsorbed on the substrate by some kind of physical force, like van der Waals force. So this VDW means van der Waals force. So if add molecules are adsorbed on the substrate, that means the surface layer, by some physical force of attraction, like the van der Waals force, that time it is called Physisorption. So depending upon the nature of the force, actually, we divide these two. And if the surface the add molecules are adsorbed by some kind of chemical force, then this is like that time that will be called as chemisorption. So in case of chemisorption, actually a chemical bond or an ionic bond normally forms, right? In case of physisorption, there no such bond formation occurs. Just a weak force of attraction keeps the add molecules onto the surface, right? Now, as this is a weak force of attraction, the enthalpy will obviously be small, and in this case, a chemical bond is forming. So, whenever a chemical bond forms, normally a high energy like releases, right? So that means the enthalpy will be quite high. With respect to physisorption, obviously, I'm just comparing those two. So, in case of physisorption, obviously the enthalpy will be small, and in case of chemisorption, the enthalpy will be high. Now, we know this van der Waals force is is a long range force, right? Means it actually like it actually the force can be feel up to a very long range. Like the intensity of the force will be different depending upon the distance, but it can be feel like it's a long range force. So that means like one can think of multi-layer formation, because there will be some kind of force, because this is nothing but a weak interaction, right? So due to weak interaction, some kind of molecules are there. So there will be some kind of molecules as well, because there will be the force will be there. The intensity of the force or the order of the force will be different, obviously, but there will be. So in case of physics options, a multi-layer formation is possible. But in case of chemistry, as I said, there will be some kind of bond, right? Let's say there's some kind of bond is actually occurring. Now, the bond is occurring between this A molecule and this S molecule. Now, if you want to have a like the second layer of adsorption molecule, so it needs to bond with A, which may not be feasible, and these two will be different. Like why A and like if A is actually getting absorbed in the surface, then it cannot be again bond with A, because it will violate the valency as well. So that's why only monolayer formation is allowed in case of chemisorption, right? Now, as there is no such kind of strong force or such kind of bond formation is required. So there is not much specific that Physisorption with respect to chemisorption, because one needs to make an chemical so covalent bond. So that times one needs to have specific, like all molecules does not form bonds with the other all the other molecules. So it is very specific which with which one can make the bond. So that means the specificity will be high. And now, as I said in the previous slide, so if we increase the temperature, that time desorption occur. Now, with increasing temperature, if desorption takes place, as there is no such bond in physisorption, so there will be no kind of dissociation of the molecule, because some with some surface of a molecule is coming and a molecule will go, right. Let's say we are talking about N2, right. N2 molecule. N2 means this kind of molecule. So let's say this is actually adsorption by the Physisorption. So it will come out as a N2, but if it is like making a bond, that times it will like break the bond. So whenever it will come out, it will not come out as N atom. Rather, it will come out as again N. So some kind of dissociation, because as bond formation is actually happening, there's a bond specific. So that times this bond needs to be break, like needs to be broken before it come out from the surface as a process of desorption. So there will be molecular dissociation takes place in case of chemisorption, but there will no such molecular desorption will be there, right? So, keeping all these things in mind, we'll come to the question. Before going to the questions solving part, I want to give a in like hint of energetics of how physisorption and chemisorption will look like. So this is a surface, right? This is a surface, and some X atom. So this is the distance. Let's say R. So some X atom is coming. So whenever the actually distance from the surface is decreasing, that time there will be a certain distance where the van der Waal will be effective, and then physisorption will take place. And after that, if we come much more closer, and if this surface and the adsorption molecules have a specificity towards making a bond, that time the chemisorption will take place. So depending upon the R, so there will be chemisorption and physisorption, and we already discussed the enthalpy change or the energy change is actually much higher in case of chemisorption rather than the physisorption. So if we go by the distance, so at a certain distance, the physisorption will take place, and then if we come much more closer, if the R actually decreases much more, then that time a bond formation kind of thing will take place, and that will we think about the chemisorption. So there will be a chemisorption. So the energy or enthalpy of the chemisorption is this much, and this is the physisorption. So clearly you can see the enthalpy is much lesser in case of physisorption. And whenever you try to dissolve, like this is the adsorb phase, and if you change the temperature, so then it will be dissolved. So how much energy it will require? This will require that much energy. So practically, the total energy of adsorption and total energy of desorption is same, provided there is sorry, like there is no, like some bond is naturally not breaking before it getting absorbed, provided. So that means if some molecule, let's say A2, is actually adsorbed, it can chemisorb, it can physisorb. But if let's say A2 is actually breaking into 2A, right? Only two A specific to it atoms. So some extra kind of energy is already need to be given. So that time it will not be the same case. I'll discuss about that. I'll try to discuss about that as well. But normally the energy of absorption and desorption is same, right? So that's what I was trying to say. If it is a N2 molecule, let's say, so if it is this is the N2, right? Let's say this is A2, not N2 even. So now it is actually at first Physisorp and then chemisorp. Now whenever you are changing the temperature, it will go to this. Why? Because some kind of dissociation energy you need to give. So this is the dissociation energy, right? So that time, whenever such kind of thing happens, that time the energy of adsorption and desorption is not exactly same. Rather, it will the desorption energy will be somewhat greater than the adsorption, right? So these things I have thought of discussing with you. Now come to the assignment part. So let's take the questions one by one. So this is the first question. So what it is? Desorption of Xc xenon atom from tungsten 411 surface is a second order desorption process, first order desorption process, zero order desorption process, none of the above. So this is a kind of informative question, right? Because you need to know, and in the lecture video you can see it. It is already discussed in the. So desorption of the Xc atom. This is a special case. So, so not sorry, this is not a special case. Like these are informative kind of questions. So what kind of the process is? But there is a logic as well. So what is this? So normally xenon, it is a noble gas, right? Just need to keep this thing in mind. This is a novel gas. Now I'll come about what is the second order desorption and what is first order desorption. Now if you know what is second order desorption and if you know what is first order desorption, then you can easily guess what will be the answer. So what is second order desorption? What is first order desorption at first? First order desorption means no if like you know about the desorption spectroscopy that is discussed already. Desorption spectroscopy, right? Thermal desorption spectroscopy. So there we get a peak position with respect to temperature. So now this is two different initial coverage. So if the initial coverage and the peak position have no relation, that time it is called first order desorption. So let me explain it in a better way. Like when the peak position does not depends upon the initial coverage of the surface, that time it is called a first order desorption. And if the initial surface coverage have a relation, like depending upon the initial coverage, if your peak position of the thermal desorption spectroscopy changes, that time it is called second order desorption. Now let's try to visualize that in the visualize the physical manner, right? So xenon, a noble metal, is actually coming into this. So if the surface coverage is not very much higher, surface coverage is not very much higher, or it is a moderately high, or even it is a bit high, like not very high surface coverage, that time your initial coverage will like if you increase the temperature, it will go normally. So if you have much number, so the intensity of the peak will be higher. If you have less number, intensity will be lesser. But the peak position, like at temperature, because desorption is actually happening like with actually following the delta G is equals delta is minus T del S. So at some temperature, the desorption will take place at depending upon the energetics, right? Because we know the enthalpy of adsorption and energy of adsorption and desorption is same. So depending upon that, we'll get just the intensity change of the peak, not the peak position. Now, if it is a very congested, let's say all the lines represent X, very congested system. That time, the nearby atom will have a repulsion, right? In so due to that repulsion, the molecule can uh, go out a bit easier than the less coverage area. But if don't like in normal case, for a like noble atom, there will be no like no dependency of the initial coverage on the peak position. Now let's say N2 disruption, N2 adsorption. So this is a N2 molecule. Whenever it comes to this, right? So this bond forms, and this bond actually disrupted. This one get disrupted. So the result will be like this. We'll get in and in. Now, whenever we are giving some temperature or heat, so that time it will again try to break, but now it will not move like separately. Again, it will try to make this bond. So, as this bond is forming, so this is kind of a associative desorption, right? Now, this is associative desorption. Now, let's say if we have a coverage, higher coverage, in right, right, and if we have a lower coverage, so whenever we are having a higher coverage, that time the two n atoms are very nearby, so that they can easily go out, right? And whenever they are far apart, that time the probability of getting a like out as n2 is much lesser. So whenever the coverage is high, the temperature will be, sorry, will be lesser, right? So if we draw the plot, in this case, so let's say, so with depending upon the coverage, this peak will shift, right, to the lower temperature region. So this is a noble metal, so there will be no such kind of associative desorption. So this will obviously be a first order desorption process, right? I don't think there will be any doubt, right? Okay. So come to the second question. So which is not true for second order desorption? Which is not true for second order desorption process? So I have talked about first order desorption and also second order desorption. Now, desorption of nitrogen is associative, that we already discussed. This is true. Now, desorption peak temperature is independent of the initial surface coverage. What we have seen, the depending upon the surface coverage, the peak position actually changes, right? Excuse me, can you mute this? Hello? Yeah, thank you. So,
Hello?
yes, yeah, hello?
Sir, I am listening to class, sir.
Yes, yes, yes. Nice. You have any question?
No, 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 sir.
So yeah. So thank you for listening. Plus, just can you mute your mic for some time? Like it is difficult to talk for me if you don't mute it.
Okay, sir. Okay, sir.
Yeah. So we have seen that the in case of associative desorption, or in case of like second order, that is same second order desorption, so the peak position is depend very much upon the initial coverage. So obviously the desorption peak temperature is independent of the initial surface coverage. That part is not true, right? That part cannot be true. So let me check the other options. Are they true or not? So here, the desorption peak temperature is dependent on the initial surface coverage. Obviously, if this is not true, then it is going to be true, and we know that, right? Because again, I am like drawing the picture. So These are the initial coverage. Initial coverage is increasing in the order. So normally this is the, and this is the temperature. So if we think about the resorption temperature, this is the first case, this is second case, third case, right? This is, let's say this. So if this is T1, T2, T3, and T4, so obviously T4 is lesser than T3, is lesser than T2, is lesser than T1. So that means the initial coverage is actually like if the initial coverage is higher, that time resorption temperature is actually lower. So it has resorption peak temperature is dependent. This is true. This is dependent upon the surface coverage. So that means resorption peak temperature is independent of the surface coverage. This option is obviously wrong. This is not correct. So that is what they have asked. Right? This will be your answer. This is the answer, option 2. Now, the fourth option, let me check it. So, the desorption peak temperature is lower for higher initial surface coverage. So, that we already discussed. So, this is also true, right? So, we know. So, what will be the answer? That will be an option 2, right? Okay. So, this is the question number 8 because these are very much connected. That's why I have decided to discuss this with that. So, which of the following statement is correct, right? Which of the following statement is correct? So let me check one by one. What is written? The peak position in the desorption curve is independent on the initial coverage for the first order desorption. The peak position in the desorption curve is dependent on the initial coverage for first order desorption. So we already discussed for first order desorption, the peak position does not depend upon the initial coverage. So this option is not true. This is not true. Now let me come to the number three. The peak position in the desorption curve is independent on the initial coverage for first order desorption. The peak position, sorry, let me come one by one. So let's come to the second option. The peak position in the desorption curve is independent on the initial coverage for second order desorption. This is written dependent for first order, so this is wrong. And here it is written independent for second order desorption. So we have already seen for second order desorption, this is second order desorption. The peak position is actually dependent upon the initial coverage. So that means this is also not true. This is also false, right? So this is false and this is false. Now it is written the peak position in the desorption curve is independent on the initial coverage for the first order desorption. So we know that it will be independent because whatever be the initial coverage, the peak position normally comes to the same position. So that means this is the right option. This is true. This will be your answer, right? Okay. So let me come to the next question. That is third question. So what are the advantages of ultra high vacuum chambers? So this is also informative question, and this is the this is the first lecture of this week. So this is the lecture number 6, I think. In lecture number 6, Professor discussed ultra high vacuum technology very nicely. So if you have not seen the lecture, I will suggest you to go to the class again and see. So what is ultra high vacuum technology? It is a like in a ultra high vacuum, where the pressure of the chamber is very low, very low. We made a chamber to keep the surface clean because any surface cannot be clean because some kind of gas molecule can be there is interacting with that or any kind of contamination will be there. So to get a clean surface, uh, devoid of anything, there will be nothing. So we need to use the ultra high vacuum technology. So so, what are the advantages? The surface remain clean for longer time, and in this ultra high vacuum, the stable solid surface are studied. Obviously, as there is no surrounding because the it is under a high vacuum, and this it is the sole purpose of ultra high vacuum is to make it clean. So obviously there is no surrounding medium, so that means no approximation for surrounding medium is necessary. So that means the answer will be all of the above. All the above points are raised are actually true for ultra high vacuum technology. So I'll again suggest you to go to the lecture number 6 and watch the video. They are actually beautifully discussed how ultra high vacuum technology is actually achieved. What are the parts of that? What kind of pumps are used? Everything has been discussed. So the answer in this case will be all of the above. The surface will remain cleaner for the longer time. A stable solid surface can be studied under that, and obviously there is no surrounding medium, so no approximation of surrounding medium is actually necessary for that. Right? Yeah. So we have discussed 4 questions. Now come to the question number 4. So in this case, I have taken very low pressure. So how much low? Normally, ultra is used in case of uh, in the order of nano to pico in this order. So what are the things like if this is, let's say this is second, let's say second, it's second. So that means 1 second. If this is 10 to the power 3 second, that time it is called millisecond. If this is 10 to the power minus 6 second, that is called microsecond. If this is 10 to the power minus 9 second, that time it is called nanosecond. 10 to the power minus 12 is called normally picosecond, and 10 to the power minus 15 is normally called femtosecond, and 10 to the power minus 18 is called attosecond. Right. So, like from nanosecond onwards, normally people tell this is ultra fast process or ultra high. So, if the pressure in case of vacuum, so the pressure is that low, that time it is called like after that. Obviously, the femtosecond or femto bar pressure will also be ultra high. So, but in this case of ultra high vacuum, this is also informative type of question. Normally, this kind of pressure is actually maintained. So these are much higher. So just by looking at the options, you can also decide. Let's say this is 10 to the power 9, 10 to the power 12. That means this is very high pressure. Obviously, so this is 10 to the power 2 to 10 to the power 6 millibar. That is also higher. But in case of 10 to the power minus 2 to 10 to the power minus 6, that means this is up to microbar millibar, and this is in the nanomilliwatt to picomilliwatt. So this is the actually answer. In case of ultra high vacuum chamber, the pressure is in the range of nanomilliwatt to picomilliwatt. And also, as I suggested you here to go back to the lecture number 6, and if you go back to the lecture number 6 as well, so you can answer this question nicely. So there, he has discussed the information with us. So what is the pressure range? Normally it is -9 to -12. And believe me, to achieve this kind of ultra high vacuum chamber is not easy. That's why we have to take very much precautions, like not precautions, like we have to adopt a different kind of technology, different kind of the setup is required, and that is called the ultra high vacuum setup, right? So this is the question. Now come back to the question number 5. So I have discussed Physisorption at the very first. Let me go back to that. So what I said about Physisorptions, molecules are adsorbed by a weak van der Waals force, like physical force is van der Waals force. Normally, change in enthalpy is quite small. Multi-layer formation is allowed. The specificity of adsorbent and surface is very less with respect to the chemisorption. And with increase in temperature, desorption takes place. No molecular dissociation can be seen. So now come to this question. Which among the following is correct for physisorption? Now we know a bit about physisorption. So it is, they are saying it is irreversible in nature. But we have seen in a surface, normally let's say a physio molecule is Xe. There is no such bond is forming. This is only a weak interaction. So that means it cannot be irreversible. We can just by changing the temperature, we can like reversibly like adsorb and dissolve. So that means this is not true. This is not irreversible in nature. Specific in nature, yeah. but that is, the specificity obviously is not much. So that means specificity is not that much. So we will also not go for that option. Now I have seen that enthalpy of adsorption. Obviously, we know enthalpy of adsorption is much higher in case of chemisorption. So that is also not true. So what it has written? Adsorbate and adsorbent. Adsorbate means the add atoms. Adsorbent means the surface are held together by weak van der Waals forces, right? So we have already discussed this physisorption normally takes place because of some physical force, normally the van der Waals force. So this is obviously the first. This is obviously the correct option, right? So option number three. So we have discussed again. I'm going back. We have already discussed what is absorption, then the energetics of absorption, then the types of absorption, and the energetics again for two kind of absorption. So from that discussion, you can easily do this question, right? So let's come to the question number six. This is a very good question. So what it is saying? Wood's notation. So let me first tell Wood notation normally tell about by applying Wood notation one can describe a unit cell in the add layer, right? So this is the add layer they have given and asked the notation for this B1 B2 this unit cell covered by this cell, right, covered by the shade. So before going to that, I'll try to discuss a little bit about how normally Wood's notation is been described. So this is a surface. These white atoms are the surface molecules, and these blues are the add atoms or add molecules, whatever you can say. So add atoms, right? So these are the surface and add atom. Sorry, sorry. Yeah. So this is the unit vector. This AA. This is the unit vector of the surface atom, right? And looking by the symmetry. So this will be a one unit cell of this surface. So this is having a fourfold symmetry and right. So the unit. So this is a FCC 100. Sorry 100 prime. So these are the lattice vector for the surface. Now we want to describe this one, this add layer. So what it will be? So normally the procedure of mentioning Wood's notation is we need to mention the first the surface. What kind of surface is it? Is FCC, and then mention the plane, right? And then give a hyphen, and then try to give some A cross B of the add layer, and if like this is, let's say this is A1 and B1, and we need to know the relation between the relation of A1 and B1 with respect to the surface vectors, surface lattice vector. If A like this A1, let's say this is A1, let's say not this is not I'm just saying if this A1 is actually 2 times of A1, then you need to write 2, and then let's say if A2 is 2 times of A1, A2, sorry, A2, A2 is 2 times of, but sorry, B1 is 2 times of A. So that time we can write 2, 2. So this is a common notation. So now what will be the notation for this surface? Obviously, you can see the unit vector for the surface unit cell and the add atom like add layer unit cell are same. All the parameters are same. This is also A, this is also A, this is also A, and this is obviously a square. So both the sides will be same. So what it will be? It will be the notation will be FCC. Let's say 100 1 cross 1. Now, if this add atoms in itself make any cone, like in any not a cone, that it is like makes any angle with the surface atoms, surface in itself, then then one needs to tell about that surface, about that angle. Okay, but if it is like if it is not like all the surface vectors and the add atom vectors are yeah, completely parallel. There is no angle it is making with the surface unit cell. So that time we don't need to mention it. Now come back to this these two. So we know this is a, right. This is a. This is also a. This is a. This is also a. So this total thing is making a making a square, and we know the diagonal of a square is nothing but root 2a, right? Nothing but root 2a. So this is root 2a. Obviously, this is also root 2a. So now, if we want to say about that, so let's say this is FCC 100, and the surface will be root 2 cross root 2, root 2 cross root 2. And now this is the surface atom unit cell, and my unit cell, what I am trying to describe, this unit cell is making angle, because this is the unit cell of the add layer. If we just think this one also, if there is molecule, obviously. So let's say this is the AOA, and this is also one. So the angle it is making with it is 45 degree. So we need to write R45, right? So let's come back to this. So this unit cell is making no angle with this, obviously. Now if this one, we know this one is A1, so obviously the total will be 2A, and obviously this is also a square, and that means this one will also be 2A. So what it will be? FCC 100, 2 cross 2, and there is no angle. Now if you write this is a wrong thing, because all these cells, there is no add atoms in between the unit cell. There is no add atoms in between the unit cell. So that means this is only corner cell, and these are the primitive cell. This is also primitive. Sorry for my bad handwriting. This is also primitive, and this cell, obviously this is also primitive. All the all the layers are in the corner set. There is no, but here one add atom layers is inside the unit cell. So this is a center, so we need to mention that as well. We need to mention that as well. So this is C. Sorry, this is C, 2 cross 2, and there is no angle, obviously. Okay. So we have written an idea about how to like denote add layer unit cell by the Woods notation. So let me go for this question. Like, so this photo I have given because it is directly taken from the lecture. So now I'll come back to this question, right? So I need to mention this. I need to mention these unit cell, right? So first look at this. The all the add layer atoms are corner share. So obviously, so I'll note the point. Whatever I am trying to, whatever I have seen here. So it is primitive, right? Now let's say how much angle it is making with the surface unit cell. Surface unit cell is this, with the lattice parameter A1 and A2, and you get it. This is a FCC 111 surface, because this is a triangular kind of thing. So FCC 11 surface means this A1 and A2 are same, right? This A1 and A2 are same. So we can write A1 is equal to A2 as well. So A1 and A2 are same. Now I need to know how much angle it is making with the unit cell. So how much angle? So here if I mention in this point, if I mention the A1 and A2, so obviously this is my A1, and obviously this is my A2, right? This is my A2, and this is my A1. So if I know the angle between B2 and A2, then only then obviously that will be same with A1 and B1. So if I make the angle between A2 and B2, this will be this. If I know, then I can know the angle of the unit cell that I am trying to the notation, get the notation of we making with the surface unit cell, right? So now how to get that? You can see this is nothing but a hexagon, right? This is nothing but a hexagon, right? This is a hexagon. Now we know for any polygon, we know the internal angle, and there's a equation as well. So 360 degree minus, sorry 180 degree minus 360 by n. N is the number of polygon. If the polygon is having similar size, like all the sides are same, so obviously all the a1 and a2 are same, that means all the sides are same. Now if we put n, so hexagon means it is having 6, so if we put n means 180 minus 360 by 6 means 60, so 120. So the internal angle of this polygon is nothing but 120 degree, right? This is nothing but 120 degree. This angle I'm talking about. Now, if you can see this, I'm highlighting this for. If you can see this, and this is making a triangle, right? This is making a triangle. Again, I'm drawing. This is making a triangle, and we know for a triangle, all the angles, that is 3, makes 180 degree. All the angles. So like the sum of all the angles is coming, it will come as 180 degree. So now this angle is 120 degree. That means this angle and this angle both. Let's say this is A angle A and this is angle B. So obviously A plus B will be 180 minus 120, right? 180 minus 120. So that means 60 degree. Now we know this. So let me change the color. We know this side and this side are similar, and we are talking about this triangle. So if these two sides are similar, obviously this angle and this angle are going to be same. So in case of a plus b, we can directly write a, because a and b are similar. So what will be the a value? Is 30 degree, right? It is 30 degree. So that means that, this is my b2, this is my b2, and this is nothing but my a2. This is my B2 and this is my A2, right? So B2 and A2 is making angle about 30 degree. So one is primitive, one is 30 degree. We know. Now what we need to know, what is the relation between B1 and B2 with A1 and A2. So this picture is a bit messy now. So I'll try to discuss with this picture. Okay. So I want to get the information of relation between A1 and B1. Let's say because A1 and A2 are same, and similarly B1 and B2 are same. So if I can get information about A1 and B1 relation, then I can get everything. So let's say we know what we know. This one is A1, nothing but A1. So that means the over this total thing. This is A1 and A1. That means the total is 2A1, right? And if we can see a perpendicular, so this is nothing but a2, or let's say for simplicity this is also a and this is 2a, right? Now we need to know this perpendicular. So for using the triangles, the great law, that is hypotenuse in this case is 2a square, this is Pythagoras theorem, is equals base square, plus perpendicular square. Let's say perpendicular is b1, this is given, so b1 square. So what will be my b1? It will be root over 4a square minus a square, obviously, so root 3a. So that means b1 will be root 3a and b2 will be root 3a2, or root 3a and root 3a, and that is uh, that is in lecture. He has not explained because it's very easy. So this I have explained how it is coming root 3 for your, like you can get it better if somebody does not get it, so you'll get it. So now I am talking about this unit cell. So now we know this is a primitive because all the atoms are shared. Now we know the angle with this is 30 degree. This is primitive. and we know the relation as well, right? So let me admit him. Okay. Okay. So we know everything right now about this unit cell. So what is the angle? That is 30 degree. This is primitive, and the relation is root 3 root 3. Now what will be the notation? Let me change the color first. The notation will be FCC. In all the option it is FCC 111, and also by looking at the picture also you can see this is FCC 111 plane. So FCC 111, at first we need to mention the surface, then a hyphen, then root 3 cross root 3 because this is the relation, and the angle we know that is R 30 degree we have seen. So this is the answer. Okay, so the option is actually maybe they have misprinted, it will be root 3 root 3. So this is the answer. Now I think this is clear to everyone. Now go to the seventh question number 7. So this one I have discussed. This is Wood's notation, right? This is Wood's notation. But Wood notation can be somehow, in some cases, we cannot distinguish between two unit cells which are having similar kind of symmetry. But by Wood notation, it can come like both the unit cell of the at layers are coming actually same in case of wood notation. So that's why we need a more general notation, that is matrix notation. How it is? Let me first discuss it. Sir also discussed it in the in his lecture. You can always go back, but I will try to give a brief discussion about that as well. So normally this is the surface unit cell and this is the Adler unit cell. Let's say so obviously this B1 and B2 we need to have the relation. So how we can get the relation? Let's say B1 is M11 into A1 plus M12 into A2. This is like we are thinking that B1 can be dissolved in two parts with M as of the A1 and A2 vector. A1 and A2 vector. And B2 can again be written as A1 and A2. So we need to find out this coefficient M11, M2, M21 and M22, right? So then the matrix, this matrix will give us the notation. How? Let's say for this unit cell. This is my A1, this is my A1, and this is my A2, and you can see B1 and B2. These are actually having same. So you can write B1 means exactly A1, so that means 1 A1 plus 0 A2 because there is nothing, and B2 you can write in A1 direction there is nothing, so that means 0 A1, and B2 is nothing but A2, 1 A2. So we got M11 as 1, M12 as 0, M21 as 0, and M22 as 1. So what will be my matrix? Matrix will be M11, M12, M21, M22. So that means this is my matrix. So how I can write the unit cell in matrix notation? So FCC 111 in this case 1001 obviously. Now come to this, right? So this is actually, if you think about the surface unit cell, this is a square, right? This is square. So this is actually FCC 100 plane. So we know this. Now what we need to get, that is B2 and B1 in terms of A1. So let's say about B1. So B1 is this one. This much is A1. So that means this much is again A1. So that means this is 2A1. So we can write 2A1 plus 0 because in this direction nothing is there. 0 B2, sorry, 0 A2, and B2 can be written as 0 A1 plus this will also be A2 and A2. That means this is 2A2. So 2A2. So what will be the matrix? This one, this one, this one, this one. So 2002, right? So now we know FCC 100 plane and 200. So this is quite simple. And what will be the answer? Obviously the 1. So here the matrix notation is directly not given, just the digits of the matrix is written. So this is a 2002, right? So this will be my answer. Other things 1001 is not possible, 1001 is not possible. And in case of FCC 110, if you think about the plane, FCC 110, let me draw that because the matrix is same. So why it is not FCC 110? So let me draw the plane of FCC 100. This is let's say the FCC, right? All the atoms in the corner, and also in all the surface there is one atom, right? Like that. Now FCC 100 plane means this is my x, y, and z axis. Let's say so 110 means with respect to z it is parallel, and other two axis it is cutting it. So this is my FCC 110 plane, right? So if we draw this plane, how it will look like that. But this, just see this. This is the FCC 100. So this is actually rectangular, and the unit cell given here is actually square. So obviously this cannot be 110 because this is 110, which is rectangular in symmetry. But here it is square. So that means this will be FCC 100. And matrix we have discussed already. So this will be the answer, right? I think you have understood this. Okay. Now let me come to the next question. This is also a very beautiful question. So this is about the coverage per primitive surface unit cell of CO on Cu100 at form at C2 cross 2 monolayer is. So the unit cell is given, it is drawn beautifully. So you need to know you need to calculate what is the density of coverage. So in that lecture it is given what is density. Density is nothing but number of atoms present in the add layer in itself by divided by the number of atoms present in the surface in itself, right? So this blue ones are surface, and this yellow ones are add, right? So now think about this unit cell. So this is the unit cell. So this is a one add point. This is also one add point. This is also one add atom, and also one add atom. Now this is corner set. So the all add atoms in the corner will be say. So this means this is a primitive cell. So the four add atoms in the corner will be contributed by the one atom, and also one atom which is not shared by anyone. That means again one atom. So total number of add atom in the add layer is 1 plus 1, that means 2, right? How it is 2? So this 4 is actually making the primitive unit cell. So this is shared by the other 4 because there will be one more surface, one more unit cell of the add layers, and so this in this add layer we are getting two atom of the two add atom. So this 4 is contributing to 1 by 4 into 4, and this one is not shared by anyone. So this one itself a 1. So we get the total number of add atom in the add layer unit cell. Add layer unit cell, right? Now, if this is the add layer unit cell, so in that unit cell of surface, how many atoms are there? So think about this blue. Okay. So blue, that means this there is 4, obviously 4 corner share, that means 1 by 4 into 4 obviously will be there, plus these 2 is shared by two atoms, and such kind of atoms are, sorry, 1 and 2, two such atoms are there, 1 and 2. This means these two atoms will be shared by 2 2. So 2 into half. And there is one surface atom as well, which will not be shared by anyone except this unit cell. So this will be 1. So total number of atom is 1 plus 1. Sorry. 1, 2, 3, 4. This 2 is also there, na? So this will not be 2, this will be 4. Right? This will be 4. So 4, 2 means 2 plus 1. So total is 4. Now this is the total number of surface atoms in the surface unit cell, right? Now we want to calculate the density. Density, let's say D, is nothing but the added number of add atoms by number of surface atoms. So 2 by 4. How much it will be? Means 0.5. And so what will be the answer? This one, right? This is the answer. So also here I have taken one more example to calculate the density or the coverage. So it will be much clearer to you. So these pinks are the add atoms, and these are the surface. And this is the unit cell marked. So in this unit cell, how many atoms of the add layers are there? 1, 2, 3, 4. So 4 are in the corner. Obviously, this will be 1 by 4 into 4 plus 1 add atoms in the middle. So this will not be shared by anyone. So total is 2. Now come to the surface. This is 1, this is 2, this is 3, this is 4. So these are not shared by anyone, right? Because this is inside the unit cell, so not shared by anyone. So there is 4 number of surface, and this is the add layer. So in this case also, density will come as density will be 2 by 4, right? 0.5 as well. So we get an idea about how to calculate the coverage or density, right? Okay. So come to the last question. So this is a very informative again, and you can find this in the lecture number 10. There, professor has given a very nice introduction of how to make a solid-solid interface. So let me first tell the question: which among the following is are the preparation method for solid-solid interface? So this is an informative question, and you can know this is a part of physical vapor deposition, and it can be done by evaporation deposition, sputtered deposition, electron beam PVD, pulse laser deposition, and cathodic arc deposition. So all the sputtered deposition, pulse laser, evaporation, all the process can be used to make a solid-solid interface. So the answer will be all of the above, right? So this is the answer 4. Answer number option number 4 is the right. So I'll suggest you to go to the lecture number 10 for get an idea of that if you have not gone through already. So this is the case. So here I have discussed all the 10 questions with you. So okay, thank you for your time. So here I'll stop discussing about that, and we'll meet in the next class. So if you have any query regarding this, you can ask me questions, or let's say we'll stop here. Okay. So okay, we'll meet in the next Saturday with the assignment 3. We'll discuss about the assignment 3, right? So okay, thank you for listening to the class, and okay, let's meet again. Have a good day. Thank you.